All right, so this is CSC200, your first computer programming class in computer science, right? Everybody, that's where you expected to be. All right, so I'm Mike Littman. I'm the chair of the department. So I teach all of our programming classes and a lot in our grad program. I know a couple of you in here, I already noticed, are part of our scholars program where you're doing a master's and a bachelor's in 4 years. So those students are going to be moving through the program a little bit quicker. So just kind of keep that in mind when you look at your classmates now. They might not necessarily be your classmates in a couple of years because they're going to be moving more quickly. All right, so when you come into the Blackboard course, CSC200, over here on the left, I have a link for streaming lectures. So this will take you to the YouTube playlist channel for where our, you could probably just grab one of the desks. Oh, we have a seat up here where you can grab one of the tables in the back, whichever you're most comfortable with. Pull one of the gaming chairs over. Yeah, so I'll put the lectures up on YouTube, and then I also have the course slides that'll be shared, and the links are already there for those, but I haven't uploaded the first video yet, so don't click that yet. I also have a link to the online development environment we'll be using. If you want to use a different development environment, that's fine. I just don't want to have to manage, 30 different people's installs of different computer programming software where we just use a website and I don't know, it's just a thing. Okay, so let's look at the syllabus. All right, so this is me. My office is right down the hall here in S112. Best way to reach me is either text me on my cell phone. That's my cell phone number. Don't call because I probably won't answer unless you're my mom or my wife. And then that's my email. And then also we use the Slack in here. In fact, let me get I'm guessing most of you are not on the Slack channel. So I'll copy that link. And then what I'll do here is I'll add an announcement. Join Slack. All right, so I think all of you would have just gotten an email. Plus, when you go on to the Blackboard, you'll see this link. Just click this link, create an account with your CUW.edu email. Slack's the tool we use in the department for like interdepartment communication. So we post a lot of internships and things like that there. Also in the CSC200 channel, I might post updates to homework assignments, or if a student asks me a question about a homework and I need to clarify it for the rest of the class, I'll probably post it in Slack. It's much more likely I'll post it there than send an email to everyone. So Slack's available for all smartphones as well as Mac and PC. Set up notifications. It'll, if you message me on Slack, it comes to me the same way as a text message does on my phone. So set up Slack so you don't miss messages from the department. Okay. Grading scale, normal 90, 80, 70, dealio. Breakdown for the class. We have Bible homework in here, as well as tech talks. Tech talks are going to be announced with dates pretty soon. I just have to wait for the computer science club to get me the final dates. But for 10% of your grade, there's already 2 assignments that are up, and I'll go ahead and show you those here. So we have Bible homework 1, Bible homework 2. These are just due by the end of finals week. I'd encourage you to do them sooner than that. I used to do Bible homework every single week, and then you had students missing whatever, blah, blah, blah. So I just give 2 larger assignments. So it's reading, in this case, it's reading 1 Thessalonians and 2 Thessalonians, and then writing a little bit of a response paper to it. So, and those are due by the end of finals week. So you have plenty of time, but make sure you cover those. That's 10% of your grade. The tech talks, what we do is we bring relatively local business leaders in the tech industry who hire a lot of our students as well as give internships to our students. We usually do 3 to 4 of them per semester. And what I do, as soon as I have the dates, I'll get them up there. So I do require them for class. If you, and that's why I give you the dates way ahead of time, so you can ask for time off of work. They're usually like at 6 p.m. at night till like 8 p.m., something like that. If you absolutely can't show up for whatever reason, I do give an alternate assignment. Usually it's like a 2 or 3 page paper or something like that. Otherwise, you get full credit for attending the tech talks. All right, so look for those dates either later this week or early next week so you can start, getting them added to your calendar. So in any case, that stuff is 10% of your grade. A majority of your grade is this programming homework stuff, which is 50% of your grade. So I'll kind of talk about that here for a second. My philosophy in education is that at the end of the semester, I have to give you a grade based on how well you've mastered the material. The way I view homework is that's practice for the big game. Okay, in a few minutes, I'm going to be talking about computer programming being like a sport, right? When you're a basketball player or something like that, you go to practice and you do all the drills and stuff, and you mess up during practice so that when you actually get to the real game, you're less likely to mess up, right? So I treat homework that way. I want you to work hard on homework. I mean, because it's your chance to practice. At the end of the day, you're the one who's going to take these skills and go get a job, right? But the idea is that I'm going to grade homework relatively easily. If you get half of it done or most of it done, let's say, but you still have a couple of bugs or a couple of things that you haven't quite figured out, I have this self-assessment thing. Is it under content or did I? Oh, I have to put it up. I do have this self-assessment that I want you to turn in with all the programming assignments that let you tell me how long did you spend on this, what problems did you run into, things like that, because especially with computer programming, you might sit there and spend 4 hours on an assignment, have very little to show, right? It's like, okay, programming is hard when you first start doing it, and even for a little bit after that, and I'll talk more about that today and why it's hard. But if you just spend 4 hours on an assignment and you turn it in and you have crap to show for it and you get a 20%, well, that's not, your effort was worth more than that, right? Even though your solution wasn't. And I'll always solve the assignments when we come to class. So you'll see the solution and all of you will understand the correct code way before you'll be able to write it yourself. All right. So I grade homework fairly easily so that you're encouraged to keep putting in the reps so that when we get to the exams, things go a little bit better. Along those same lines, you have a midterm and a final exam, each worth 20% of your grade. My policy is if you do better on the final exam than you did on the midterm, I'll replace your midterm exam grade with whatever you got in the final. Sometimes it just hasn't clicked by the midterm. All right. So we've had students before get 20% on the midterm, come in and get a 95 on the final and end up with a solid A in the class because that 20% turned into a 95. That makes sense? So I give you every opportunity to succeed in the class. Just keep in mind, you're probably going to be spending a good amount of time, especially as we get farther into the course, working on the homework, not because I'm purposely giving you homework that takes a lot of time. It's computer programming takes a lot of time when you're first getting into it. Next semester, you'll look back and say, why did I spend 5 hours on that? You're like, I can write it in like 8 minutes. And that's going to happen. And it's what's going to happen during this class is you'll have a homework assignment. You just spend a bunch of time. You come into class and we solve it in class in 10 minutes. You're like, really? It's going to be kind of a frustrating thing. But so just mentally prepare for that. Okay. The rest of the stuff you can read through. Just, I guess, it lists the different units and stuff. But I deviate from that sometimes. The class kind of grows organically. I just, whatever comes out of my mind and mouth at any point in time is just kind of, that's what we're covering that day. All right. So any questions about the class, grading for it, any of that jazz? Okay. Like I said, I do record every class and I do the recording through Zoom. With that in mind, if you are sick, let's say, you would be able to attend class live using Zoom without actually attending physically here. Now, having said that, that should be the exception. That's not giving you permission to not show up to class and instead be on Zoom, but it is a backup plan, okay? So if you did need to go out of town for a couple of days or you were homesick, whatever, you won't miss class because of it. But I also record the lectures and upload them to YouTube. So if you need to go back and review stuff, you can also do that. Or if you miss a class for a doctor's appointment or something, similarly, you can go and rewatch the lecture. All right. Questions about any of that junk? Okie dokie. So let's go ahead and open up the slides. All right, and I'm probably going to add and remove stuff from the slide set. So what I do is I just kind of start with the slides that I've used in the past and let it just grow organically from there. Here's that self-assessment template I mentioned to turn in with all your assignments. The programming assignments, you don't have to turn it in with a paper. I assume you're not going to give me, for a 2-page paper, you're not going to give me a blank document and have to explain yourself. I'll probably be able to read the paper and find out how well you did, but programming is a little bit of a different beast. Again, my email address, my cell phone. There's the Slack thing. All right, so one thing I like to do, actually, out of curiosity, how many of you have had any sort of computer programming before? Okay, so roughly half of the class, something like that. Now, I do make the assumption you've never seen programming before in here. It's still going to be hard, okay? But I'm not assuming you're coming in with any knowledge. But now one thing that I like to say, so I've been programming for a couple of minutes. I started programming when I was 9. And my doctoral thesis was on writing a programming language. So I've been doing this stuff for a while, and this is a truth, is that programming is the skill set. The language does not matter. So those of you who just raised your hand, whether you've done Python or Java or JavaScript or C# or whatever, all of these languages are the same. It's the computer programming that's the skill set. And that kind of comes off this slide. I like to kind of ask the question, how do human beings solve problems? And you could probably get into the minutia and come up with a little bit broader, 5 or 6 different ways. But, I say we use our memory. So we have to remember stuff. We ask a lot of questions, and then we repeat tasks over and over again. That's kind of the go-to moves that people use when they're solving problems. Imagine, they make light of this in some movies and stuff like that, where, somebody has like short-term memory loss or something. The one that comes to mind is like the movie, I think 50 First Dates or something like that, where, there was this guy who only remembered the last 8 seconds of something. And he kept reintroducing himself to people. But if we don't have our memory, that's pretty debilitating, right? If I say, what's your name? You're somehow doing this little lookup in your brain and spitting out, oh, my name is Mike. Something like that. Well, you probably have a different name, and there might be a couple Mikes in here. Who knows? But, that's kind of the punchline. So anyways, these are the ways that human beings solve problems. So what I'm promising you is that 100% of programming languages will have facilities for these 3 things. They'll have some way of remembering things, usually through variables. They'll have some way of asking questions. Usually this is conditionals like if statements. And then they'll have some way of repeating tasks. These are through loops or functions, procedures, things like this. All right. But 100% of programming languages will have facilities for doing these types of things. So that means if you already have computer programming as a skill set, and I show you a brand new language you've never seen before, first of all, there's a pretty good chance that language is derived from another language you have seen before. And we'll talk more about that here in the first couple of days of class. But if it's a language you've never seen before, all you have to do is figure out, well, how do I create variables? So how do I remember stuff? How do I ask questions? And how do I write loops and write functions? And if you just realize those couple of things, you can already solve a huge set of problems with that language. day one. Sure, that doesn't get you some of the extra bells and whistles. Some languages lend themselves to certain kinds of problems more so than other ones because they have some built-in libraries for doing fancy schmancy stuff. So through using language, you kind of maybe will learn about those things. But in terms of just writing simple logic type stuff, the language does not matter. All right, so here's the slide that kind of talks about those mappings. Every language will have facilities for these guys. Okay, so those of you who raised your hand saying you've had some programming before, how many of you counted HTML as that? A couple people probably. So just to kind of prove the point here, so HTML is this, it's a language, not a programming language, but it's a language that we use to express web pages, right? It's a tag-based format. But HTML does not support remembering things. It does not support asking questions. It does not support repetition. So the idea is it's actually not a programming language. It's what I call a data representation language. A web browser knows how to interpret an HTML document and turn it into pretty pictures and text and that kind of stuff. So not a programming language, but that doesn't mean it's unimportant. It's just not solving that, that problem. All right, so why is programming actually hard? Now, some of you might catch on fairly quickly. Some people's brains just work that way. But in general, I suspect many of you, if not most of you, are gonna struggle. You know, you're gonna feel like, hey, I'm spending way more time in this class than I'm spending in my other classes. And why? Well, first of all, the juice will be worth the squeeze. You know, you can go out and get very high paying jobs with a computer programming background. And it's even more so now post COVID, because now so many businesses that were forced to go on, allow their workers to work remotely, have now maintained letting their workers work remotely. So typically the starting salary coming out of our undergrad program, if you're going to work like in the Milwaukee area, it's called this Midwest dollars, is around $75,000 a year right out of school. With a master's degree, it's about $85,000. Now you go to one of the coasts like New York or, you know, Los Angeles or something like that. Well, all of a sudden that 75,000 turns into 110,000, but your apartment is costing 8 times more than it costs here. So, you know, it's really the same salary once you calculate in your expenses. But an interesting thing that's happened more over the last couple of years with this COVID thing is we have several students who've recently graduated who live in Milwaukee or nearby and work for companies in like New York City. So they're making $100,000 a year, which is saving the New York City company 10 grand a year. And they're making more money than they'd make here. Everybody wins. And they fly you out to New York, you know, once a month or something like that for meetings or whatever. But, you know, lots of cool type stuff with that. We have another former student who has he works for a company in New York, but he just travels around the world. So he lives in these different countries for 2 or 3 months at a clip and just works as a software engineer in whatever country he's currently in, which I would think would be cool for maybe 6 months or a year, but then that might get kind of old, but still kind of fascinating stuff. So this profession that you're training for is a pretty good one, assuming you're happy doing it. Everything's not just about money. You know, if you just absolutely hate programming and you're not going to want to spend your rest of your life doing this, even if it pays you well. So I can certainly help you navigate that. But, you know, the idea is that everybody in here should expect that programming is going to be difficult. And the reason for that is because all of you are too good at solving problems. And I mean that sincerely. Human beings are so good at solving problems that we have a weakness in being able to articulate how we solve that problem. You know, I kind of give a simple example here, but the broader example that I like to use is like, let's say you're, you know, walking in from your dorm or from the parking lot here, going through the halls, and I'll ask the question, you know, how many of you bumped into any walls or people as you were coming to class today? You know, and you usually get 1 or 2 people that whatever, but in general, you know, when you see people walking down the hall, they're not even paying full attention. Their faces in their phone, they're playing games, they're texting, whatever. It's not even worth your full attention to walk, right? And when you think about the complexity of something like walking, I mean, that is an incredibly complex thing. You're firing certain muscles and, you know, catching your balance, doing all these things. I mean, there was probably thousands of moving parts when it comes to the accomplishing walking. So if I asked you to sit down and write me a list of every single thing in the right order that has to occur to successfully walk 10 feet down the hall, we would not be good at doing that, right? Because a lot of what we do when we're walking, we're not even thinking about. Hence the thing that we have time to text. Okay. We're too good at solving these problems. You know, we kind of practiced it until we kind of figured it out. And that's actually some of the things with artificial intelligence these days, the machine learning type stuff where we're creating neural networks for making decisions. Those are trying to mimic the way human beings solve problems by, instead of programming something to work discreetly, you're training a neural network to, I guess, make decisions for you. My first experience with a neural network was years ago. And so now we have tools from like Google and Amazon that allows you to like create a neural network very easily. But back then I was in an artificial intelligence class and we had to program our own neural network and then train it for some data. So, you know, what we did, without going into the details of it, is we basically created this thing and then trained it with the 1 through 5's multiplication table. You know, 1 times 1, 1 times 2, yada, yada, yada. And, you know, so what happens is the neural network makes a guess. You know, you feed it the inputs, it spits out an output, which is just a guess initially. If it got it right, you do nothing. If it got it wrong, it's like you slap it on the wrist, you tweak the numbers a little bit, and you do that thousands and thousands and thousands of times until it gets all or close to all of those correct. Because I trained it on the 1 through 5's multiplication table, right? So now I have this neural network that's been trained on that data. Now I gave it data it had never seen before, the 6 through 10's multiplication table, and it got them all right. Never seen the data before, but I trained it on the pattern of multiplication. It's just fascinating, but that would be a different approach to problem solving, and that's where machine learning is becoming a very popular thing. So for problems, complex problems that might be difficult for a human being to articulate how to do this, multiplication isn't necessarily one of those problems. It was just a good example. But some problems, we would have problems dictating how we do it. And we're never going to be able to write a computer program that fully captures that. So we're going to be relying on this other field, artificial intelligence and machine learning, for accomplishing those things. You know, that's where the self-driving cars and stuff live. You know, there's not a piece of discrete software in there that says, okay, if stop sign, do this. And, you know, it's basically having, you know, millions of people driving their car, and it's reading everything that you're doing and trying to figure out, hey, how do you drive a car? And it's pretty good on the interstate, but it's not so good if you just like get in your car and say, take me to Starbucks or something. I have a Tesla and it's pretty sketch. Yeah, I have the beta for the full self-driving, but I tell you what, I mean, it's interesting whenever a new piece of software comes out and I say, you know, I put in an address and I say, take me there, and it'll back out of my driveway and everything. But I mean, it gets a little bit weird around like making right turns or staying in its lane when it's turning, when there's two, it's bad. In some cases. So it's academically interesting, but the interstate driving is pretty good. That makes life a lot easier. All right. But in any case, human beings are so good at problem solving, we have trouble articulating the details. All right. And in order to write software, we have to retrain our mind to break problems down into little tiny baby steps so that we can use the programming language to tell the computer what we want it to do. The language is not going to be the difficult part. At first, when you think about code and the syntax of C or C++ or Python or whatever, it's like, oh, well, this looks like gibberish, whatever. But very quickly, you're going to find that the syntax is not really the difficult part. It's knowing, well, do I need to, how many things do I need to remember here? Let's create some variables. What questions do I have to answer? Do I need to ask them multiple times? Do I put it in a loop? Things like that. It's going to be getting used to the problem solving, almost like writing a recipe. You were teaching somebody how to make like a peanut butter and jelly here. You know, you got to write down every little step. For a human being, sometimes we can fill in the gaps, right? But for a computer, they're never going to be able to fill in the gaps. So you're always going to have to get skilled at breaking a problem down into little tiny steps. And it also then limits the complexity of the problems we're able to solve as human beings. How many of you are gamers, like video games, Xbox, PC, whatever? So you see some of these, newest, latest, greatest, tons of explosions, high definition graphics. You look at these video games and you might say, oh, that seems really, really complex. I'll never be able to program that, or that must be, millions and millions and millions of lines of code of really difficult stuff. All hard problems, all hard pieces of software are made up of a bunch of easy parts. If you were to look at the source code, you're going to see variables, you're going to see if statements, you're going to see loops. And for most of our video games these days, they're using tools like Unity or Unreal Engine, game engines that allow them to effectively create a video game without having to program the physics. Physics is, like if you throw a baseball, it falls out of the air eventually, right? And that's physics acting on it. If you had to program that, it's not going to look all that real. It's going to add a lot of complexity to it. Well, now we have software libraries that do all that for us. Okay, so writing a video game is actually not that complex. Probably the hardest part is coming up with your storyline and deciding, what's the right kind of gameplay and stuff like that. In fact, in the second semester programming class, when you get into 250, for the second half of the semester, we actually use Unity and write some 3D type game stuff. And you're going to see when you get in there, it's not all that hard. You're just learning the tool and you're using C# programming, not a big deal. Let's see. Kind of already talked about that. Somewhere in here. Okay, yeah. So I like to use this analogy that programming is like a sport. If you play any sports, basketball, baseball, tennis, a lot of my international students in the grad program, we talk about cricket, kind of like a baseball type game that they play. Even if you're good at one of these sports, soccer or something like today, when you first started playing that sport, you were probably not very good, right? And I'm an avid golfer, and I'm a pretty decent golfer. And I can go out and give somebody a golf lesson, and I can, show them how to hit a pitching wedge or something like that. And they might academically understand what I just taught them. But until they've hit 1,000 pitching wedges, put the reps in, they're not going to be very competent at it, even if they academically understood what was going on. Okay, replace golf with whatever, sport or whatever is kind of your cup of tea. Or even video games. Somebody can understand the controls of a video game, but until they played for a bunch of hours, they're probably not going to be very skilled at it, right? Okay, programming is like that. It's not something you can just cram the night before an exam and expect to come in and perform well. Because to actually write software, even if it's only 3 or 4 lines of code, requires that you're confident in how you solve problems with programming, and you won't get confident unless you put those reps in. And that's the purpose of having all the programming assignments and having to spend time in them, and also why I grade them fairly easily. So you're encouraged to spend that time and get good grades out of it, and then show me what you've learned on the exams. All right. Let's see. Getting into the CPU stuff. Kind of mentioned this, computer programming is like a superpower. You can make a pretty good living using this stuff. Talk about, where's the CPU in this? Okay. Let's go this route. All right, so when you're writing software, one of our goals is to create an algorithm to solve the problem. You can replace the word algorithm with the word recipe. So you want to write the step-by-step instructions to accomplish something. So one thing that happens with really all programmers, but specifically inexperienced programmers, is you'll read the question being asked, and then you'll immediately dive into code and start trying to write the code for it. you're going to be much better off drawing some pictures first, things like that, writing in English. Okay, I need to do this, then I need to do this, then I need to do this, writing out a recipe for how you're going to solve this problem, and then going in and translating each line of your recipe into the appropriate code. And you'll find out that those things are very, very similar. The skill you'll have to get practice is making sure you have enough detail in your recipe to make sure a computer doesn't miss steps, even though a human being might fill in the gaps for you. So you have to get skilled at creating these algorithms. So usually the idea is you read the problem, make sure you fully understand what the problem is asking you to solve. Then you maybe draw some pictures, write out a bulleted list of things that need to happen. Then you can go and start writing some code that matches that. All right, so I mentioned earlier that programming is the skill set, the language doesn't matter. Having said that, there are a bunch of different types of programming languages. And when you learn a new language or you're exposed to a language, it is beneficial to be able to kind of pigeonhole it into which type of language is this, because that's going to give you a decent starting point of how that language might behave. So the next several slides, we're going to be looking at different types of programming languages from different lenses. All right, so these are kind of our, how do we classify a programming language? We have the idea of a high level, low level, machine level language. We'll talk about what the difference is there. We have compiled and interpreted programming languages. We'll talk about the difference there. We have loosely typed and strongly typed languages, general purpose versus domain specific languages, and then we have object-oriented versus procedural programming languages. There's also a third one there called functional programming languages, and you actually get exposed to one of those in the language theory class if you're the software engineering concentration. CSC200, we use that to write a programming language, but I leave it off of here because it's in context for us, it's not all that helpful. All right, so we have all these different kinds of programming languages depending on what lens we are looking through. So let's talk about the first one first. High level, low level, machine level. All right, how many of you know what a CPU is? We've all heard of a CPU, right? Okay, well, I'll tell you, we already know what it stands for, Central Processing Unit. What does it do? How does a CPU work? You hear things like, oh, it's the brain of the computer or whatever, but can anybody kind of tell me how you think a CPU actually works? What is it? Go ahead.
It's part of the computer that actually processes the instructions.
Okay. Okay. So the CPU is going to receive individual instructions and it's going to actually execute those instructions. Okay. Now, the question is what do those instructions look like when they get to the CPU? So whether you're writing C code or Java code, Python, whatever, these are all high level languages. These are languages that benefit the human being. All right. So let me just get to the slide. It's going to be. Okay. Yeah, this is the guy. So high level languages, these have a one-to-many relationship with the CPU. What that means is the human being writes one line of code in some high level programming language, and some other tool turns that one line into potentially hundreds of lines of code, hundreds of instructions, like he said, that the CPU will execute in order. Okay. Certainly, as a human being, we don't want to have to write hundreds of instructions when we can write one line of code. Okay. So we're greedy. We'd rather make it easier to program, spend time writing some sort of translation program in the middle, either an interpreter or a compiler, that then turns our high-level code into low-level code that the actual CPU understands. Okay. And most of the languages you may be heard of or the language you'll ever use are all going to be high-level languages. Every now and then in industry, you might work with a low-level language if you're working on the programs for like a dishwasher or some sort of embedded system. But in general, I would say 99.5% of all jobs in computer science are going to use some high-level language. And most of the languages you've ever heard of are high-level languages. All right, so now what's a low-level language? A low-level language has a one-to-one relationship with the CPU. So a low-level language still looks like English-y type stuff. So it's words that you can read, okay? But it's much more granular. You're doing little tiny steps of the problem instead of writing 1 or 2 lines of code in a high-level language. Not necessarily a waste of time. In fact, a good example of where low-level code can still sometimes be used is in the video game industry. So, a lot of our modern video games, if they're not using one of the newer game engines, they might be still written in like C++. Now, these high-level languages, as we're going to run into, sometimes force us to write things a certain way because they have rules and we have to abide by those rules. Well, let's assume that this language says that before we can use this variable, we have to make sure that it has some value in it. Well, as the programmer, we might say, we know that it will always have a value in it, even though the programming language doesn't necessarily know what we know. So it might still force us to say, if it doesn't have a value, throw this error, otherwise go and do something else. Well, at that point, you're asking 2 questions. You're asking the question, does this have a value? That slows things down. With video games, especially certain aspects of the game need to be very, very, very fast. Maybe you walk into some room where there's 1,000 things going on at once, and it's putting a lot of stress on the graphics card, whatever it is. If you can reduce the things that are happening by 1 or 2 questions, that adds up. Okay, so if you happen to know that you don't actually have to ask that question, is there a value in there? Because there will be, otherwise the game's going to crash regardless, something like that. You can go in and modify the low-level code that was output by the compiler for that video game and modify just that section to remove a couple of questions. These are areas where a low-level coding might still be somewhat common in very specific cases. All right. But generally speaking, human beings are not going to like low-level code. Okay. And we're going to actually look at an example of low-level code here in a minute. Then we get to the other one, the machine code. Just zeros and ones. We like that even less. You get the little 2-button keyboard, just tapping it out. We're going to make a lot of mistakes, first of all, and we'll just quit the job then, an hour later. But let me kind of give you an idea here. Let's do hello world. Yeah, this will work. All right, so we can all see the code there. All right, this is low-level code. All this program does is it accomplishes putting the phrase hello world on the screen. And what you're going to see as I walk us through this is still using power tools. So actually what should be here is probably hundreds and hundreds of lines of code that accomplish that. And I'll point out how that works here in a second. But ultimately, you would have had a computer program where, let's say it was in Java, you would have just typed in system.out.println hello world. And then you would have compiled it, and the compiler turns a high-level language into a low-level language, and you get this. Okay? Now, before I go through this, what's an operating system? Go ahead.
This is the operating system, the software that actually handles the hardware.
Yep. Good. Yeah. Because I mean, as human beings, we certainly don't want to sit there with like a couple of metal objects, like touching 2 pins together to get electricity to flow through to solve some problems. You look back, most of you are taking the 175 class right now as well, which is like an introduction to computer science. So more of a broad introduction to computer science, where this is the coding class. And you're probably going to look at some of these, old time computers like UNIVAC and EDVAC, which take up like the size of a gymnasium. and you had people physically walking up to the machine and manipulating vacuum tubes and touching a piece of metal here and a piece of metal here to get something to happen. That's not how we use our computers today, right? We know that inside of this laptop is a machine, and there's going to be circuit boards and other fancy schmancy stuff that some smart person put together for us. We don't want to have to deal with the hardware directly, so we rely on this piece of software that sits between us and the hardware to make our life easy. All right. Now, the operating systems that we're used to, are going to be like Mac OS, Windows 10, 11, whatever. Linux is another one. The reality is all those things would be called distributions. So like Windows 11 is actually a distribution. The actual operating system is something called the NT kernel. And then sitting on top of that is all those pieces of software that you expect to be there when you first install Windows, like Notepad and a web browser and things like that. Okay. The ability to organize your files, having, folders and things like that. All right. But under the hood, the actual operating system is NT kernel. For Mac, the actual operating system is a Unix-based kernel based off of something called OpenBSD. For Linux, it's called the Linux kernel. Okay. Those are the actual operating systems, and the actual operating systems under the hood, they know how to do various things. Like, for example, they know how to write something out to the screen. So whoever wrote that operating system has already written a whole bunch of a really difficult, complex program that to tell all those pieces of hardware how to ultimately get a couple of pixels of light to appear on the screen. There's a lot of stuff going on there behind the scenes. So operating systems do a lot of work for us, and that's why our computers have gotten so much smaller, where now you got the smartphone that's 100 times more powerful than the spaceships we used to send into space. It's pretty ridiculous. All right, so understanding that an operating system does a ton of heavy lifting for us, this program that we're looking at here, when you compile, so we have this thing called a compiler. If you remember back in this slide here, kind of the different ways of classifying a programming language. One of these things was a compiled language versus an interpreted language. So compiled languages, they take your high level code and they translate it into code that's understood by the computer before it runs. An interpreted language does it on the fly. Okay. Typically compiled languages would be considered faster. Interpreted languages would be considered slower, but our computers are so fast, most of the time we're not going to notice. So that part doesn't necessarily matter that much. But just talking about this compiler piece here for a second, a compiler translates high-level code into low-level code. But a compiler needs two pieces of information in order to do its job. It needs to know, well, what language is your high-level code in? If it's Java, you would use a Java compiler. If it's C++, you'd use a C++ compiler. If it's C#, you'd use a C# compiler. So it needs to know the programming language, but it also needs to know your target operating system. When you compile this, are you creating an executable that runs on Windows? Are you creating an executable that runs on Mac or runs on Linux? Something like that. It needs to know both of those pieces of information in order to give it the correct low-level code output. All right, and we're going to see that here in a second by walking through this code. So for this particular code we're looking at here, I believe the source of this would have been probably C programming language. Doesn't really matter for this, but the target is the Linux kernel. So somebody wrote hello world in a C program and then compiled it. And ultimately, when they compiled it, it creates an output file that runs on Linux in this case. So it had to know the language C and it had to know the destination operating system. And if you want to kind of see the deal here. All right, so I'm going to create a little hello world program real quick in C. All right, So this will be a high level language. I'm just using a command line based text editor. You could write this in Notepad or anything like that. All right, so all right. So I wrote this program, Hello World. You just saw me write it. That's the entire high level language for printing out Hello World to the screen in C. And a lot of this is fluff, right? You know, this stuff up here says, give me access to the things that allow me to do input and output. That gives me access to this printf function to print something to the screen. We'll talk about main. All programs begin and end with main, but most of this is fluff. Our real code is that line right there. That's what ultimately prints something to the screen. Okay. So for the sake of this argument, we're going to say we wrote one line of code. Okay. So then I came out here and I compiled it. So I used this tool called GCC, which is preloaded on the Mac. If you run Linux, it's also preloaded. Windows, you'd have to install it. But most of the time for us, we're going to use a tool that makes programming easier than this command line stuff. So really what I'm showing you here is maybe how it was common to write code, you know, in the 90s or something like that. Not that people don't still do it, because sometimes you're remoted into machines that are running Linux without a graphical user interface and having to deal with a terminal like this. So that is important. I know in 175, Dr. Wald takes you through some terminal exercises, but our focus in here is on the programming aspect on it, of it. So modernly, you'll usually use some sort of fancy text editor that color code your programs and automatically indents for you and all sorts of stuff. You won't have to do this kind of thing. To compile, you hit a little play button and it magically compiles it and then spits out the result. I'm showing you a little bit what's behind the scenes here. So I wrote some code and then I used the GNU C compiler. That's an open source C programming compiler. So that's what GCC is. GCC is a compiler, and when I use GCC on this computer, the job of a compiler is to translate from a high-level language, in this case C, into a low-level language. In this case, it would be assembly language for the Linux operating system for the particular architecture of this, which is a, I think this is running Intel Core i9s. Yeah, so this is an 8-core Core i9 processor in this machine. So pretty hefty processor, but this is going to make effectively Intel-based assembly. You know, he mentioned earlier that what does the CPU do? A CPU has these instructions. Well, if you get a computer today, Apple's actually the better example today because now they're switching back to their own processors again. There's a whole history story there. At some point, I'll tell it. But because Apple used to run on PowerPC processors versus Intel, and then they switched to Intel, and this is when they almost failed as a company 2 different times. Now they're going back to their own processors again, which actually are really good. It's going to be kind of the future of processors, but Intel will have their own equivalent type stuff. But in any case, right now, I have my MacBook Pros from 2 years ago, and this year's MacBook Pro has a new processor in it called the M1 Pro or the M1 Max, which actually is a different architecture. Okay, so you can think of it as like an electric vehicle versus a gasoline vehicle. The actual engine is a different kind of animal. Okay, so a M1 processor understands this list of 100 instructions. A Intel processor has this list of 100 instructions it understands, and it's going to have a lot of instructions that mean the same stuff, but they're technically a little bit different word, the syntax for that low-level language. So the compiler needs to know what's your source language, in this case it's C, what operating system am I targeting, and what kind of processor is on that operating system. It's usually called the architecture of it. So when I run GCC here, it's going to notice by this extension, this is a .c file, that this is a C programming language. It's going to know that, okay, your target operating system is the Mac OS and that your architecture is Intel. So it's going to compile this, and ultimately it's going to, we see no output here, but what it just did is it gave me this file called a.out. That's my executable file that will work on this computer. All right. So if I run that, there's my hello world. That's the execution of my program. So that's evidence that my C program was written accurately. My compiler turned it into low-level code for this architecture, for this operating system, and then I just ran it. Make sense? All right. So what we're going to look at on this website is effectively the contents of that a.out file. You got to use a special kind of editor to view it if I try to view it on here. So if I do like cat a.out, you know, it's blah, 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 gobbledygook. But if you use the right kind of editor, you can actually see the assembly code. So for our example here, let's assume that this is the contents of that a.out file. Okay. Now you'd look at this and say, okay, well, even if we only count the C program as that one line of code, even though there's kind of 4 or 5 lines of fluff with some curly braces and stuff there, this isn't drastically longer, right? It's maybe a little bit less, I don't know, Englishy, like you don't actually see a word that's something that says print in there, but it doesn't look ridiculously huge. The reason for that is this, what we're looking at here is heavily leveraging the operating system. So what we're going to see here is how assembly kind of works with modern operating systems. So I'm going to walk through this. So first of all, remember, we human beings solve problems. We remember stuff, we ask questions, and we have repetition. So we have a section down here called data where we're remembering some things. So I have 2 different variables. One's called message, the other one's called length, LEN. So message is going to be my phrase, hello world. The length, this is how many characters are in that. Don't worry about why that's important for this. Just, I'm remembering those 2 pieces of information. What's the message? How long is the message? Okay. Remind me later. All right. So now we'll go to where it says start. That's where the program will start. So these first 4 things, we use this this function's called move. And what move does is it moves one value into a what's called a hardware register. Okay, a hardware register is on that physical CPU, on that architecture. It's a piece of memory, really, really, really fast and usually pretty small memory that can remember something. So it's basically a hardware-based variable. And processors, depending on their lineage, how recent they are, they might have 4 registers, 8 registers, 64 registers, and those registers might be of different sizes, 8 bits, 16 bits, 32 bits, yada, yada, yada. If you don't know what I mean by all this bit stuff, you'll know very soon because we're going to learn all the different bases here before we even start writing code. You'll be converting hexadecimal to binary and all this stuff and realize that's not a very difficult thing either. All right, but you have all these hardware registers. So in here, you can identify the registers. EDX is a register, ECX is a register, EBX is, EAX is. So these are the names of memory modules that live on that physical piece of Intel processor. Make sense? Now we're already getting a little bit into the weeds here. Like, okay, well, I'm already kind of happy we don't have to write code like this, but I'm telling you, this is the easy assembly code. Again, you won't have to write it, but we want to appreciate what's happening for us. As human beings, we like to use power tools, right? And that compiler is a power tool, and hopefully I prove that to you here. So these first 4 things here, what we're doing is we're moving pieces of information into 4 different registers. So I'm moving the length of my string into this place on the processor called EDX. I'm moving the actual message itself into this place called ECX. I'm randomly moving the number 1 into EBX, and we'll talk about that in a second. And we're randomly moving the number 4 into EAX. Now, if you look out here to the right, this is Where do I want to write this out to? Effectively, what we're doing is we are staging the processor in preparation to ask the operating system to put something on the screen. So the operating system needs 4 pieces of information to put something on the screen. What is it? How long is it? Where do you want me to write it to? Do you want me to write it to the screen, to a file, whatever? And then what tool do you want me to use? In this case, we're using syswrite. So syswrite is really, so this number 4 here, this corresponds to something called a system call on the operating system called syswrite. And syswrite knows how to write something out. Syswrite needs 3 pieces of information. What's the message? How long is it? And where do you want me to write it? This is a power tool provided to us by the operating system. If we didn't use this power tool, we would have to have all the assembly code associated with syswrite sitting right in here, which might be hundreds and hundreds and hundreds of lines to tell a computer all the little things that need to happen in order to get pieces of light onto the screen. Okay. So EAX is going to hold, what is it do we want to do? EBX holds, where am I going to write it? What am I writing? And how long is it? And then right here, what we do is we interrupt the processor and tell it to let the operating system take over. So what we're doing here is we're moving 4 pieces of information into 4 different registers. And then we're saying, okay, I've done what I'm doing. Operating system, in this case, Mac OS, you take over. And what does the operating system do? It immediately goes and looks at this hardware register, says, oh, okay, you want to do magic trick number 4. Okay, that's syswrite. Okay, I'm going to need 3 pieces of information from you. So hopefully you put them in the right places. It's going to look for the length in EDX. It's going to look for the message in ECX. It's going to look for where do you want me to write it in EBX. Those specific places. It's going to go to those very specific places to get those pieces of information. So the compiler needed to know what were the right places to put those things. Okay, compilers are really hard things to create. Okay, so they're power tools for us for sure. So when we tell the computer, the operating system to take over, it's going to read all these things and say, okay, I got you. It's going to spit the message of length len out to the screen, standard out, using syswrite. So we would see hello world on the screen. Then we come back. And really, from our perspective right now, you can just say, okay, the program's done. This last part's really more just like a, I don't know, a finishing move type thing. It's not really overly important for the code, but it's kind of will be always be the last piece of any problem. So we return to our assembly code here. We overwrite what used to be an EBX with a number 0. This is actually going to be the exit code. This is less common today, but in older computers, when you ran a program, like for instance, you actually saw me do it here a few minutes ago. So I'm sitting at a command line here and I type in ls, that has an output. And I can use that output that came out of there for different things. So sometimes I might want to know if a program succeeded or not. So if I were to, in a script, ask, did ls do its job? It would return a 0 if it did, or a 1 if it didn't, if it functioned correctly. Sometimes we care about that when we're using Linux-based terminals. That's a more common thing. Windows, this is something you probably never even experienced. For many of you, since your first operating system was probably what, Windows 8? What's the oldest Windows you remember?
XP.
Windows XP? Okay.
XP.
Yeah, so I mean, you're already well into the operating systems that are double click based, right? You know, some of you may have opened the command line before to run some script or something, but in general, you use your computer with a mouse or trackpad and double click on crap, right? This is kind of what's actually happening under the hood. I promise you it's still happening under the hood, but you're not actually seeing it. All right, so after we've actually gotten hello world to the screen, what we do is we move a 0 into EBX, basically saying everything went fine. And then we overwrite EAX. Remember, EAX was the register that held the what is it that we want to do. So before it had a 4 in there, which is sys write. Now we're putting a 1 in there, which is sys exit. That's the operating system call that says, okay, we're done, kill the program. Reclaim the memory the program was using, yada, yada, yada. So just like we did up here, we interrupted, which calls the operating system. The operating system immediately checks EAX to find out what did you want to do. It notices, you put magic trick number 1 in there, so you must want this program to exit. Then it checks EBX to see what was your exit code, and then it ultimately returns that, does whatever magic needs to happen in order for the program to ultimately die and return its value. Okay, if that's useful to anybody. Okay, so that is a low-level program that's written in, this is Intel-based assembly language. So this is what assembly would look like, a low-level code for talking to any Intel-based processor. And specifically, this is if you are doing this in terms of the Linux operating system. So even though this isn't overly complex or long, it's not like you wrote 1,000 lines of code, this is nowhere near as friendly as that. This looks a little codey, so it might not be super new to you, but this, you could look at this and have a decent idea as, okay, that's probably printing hello world or something, right? This looks like English, that other thing looks like something where it's like, I'm going to change majors. All right. So what I'm telling you is you will very rarely have to do something like this. Now, having said that, next semester, you're going to have the 325 class, which is computer organization. You do write assembly in there, but you actually write significantly simpler programs than even this, because the focus is really how do computers work. It comes with this little lesson telling you what a CPU is and how they work. It goes into more depth in there. But I gave you plenty of information in here with dealing with binary and stuff like that, that class will be fine, but just be prepared that you will get into the weeds in that class, but you're not going to be like writing video games in assembly. You'll be like moving things into a couple of registers and doing math with them or something like that. Okay, go ahead.
I was told that like programming and assembly is like building a skyscraper, like great to stand. Would you say that?
Yeah, I mean, I would say programming in machine code, zeros and ones, that's probably a very close thing. Assembly's not far from that. Yeah, I mean, that's not unfair. It at least gets the point across that this is probably not something you're going to overly enjoy. Yeah. And the thing is, as human beings, we like power tools. And this is true in our everyday life. I mean, a lot of times when we're looking at some of the programming tools we're using, we can look at how we solve problems in daily life and see how we've evolved over time, right? We used to walk everywhere, then we went horseback, now we have cars, now we have faster cars, and now we have airplanes, we used to do boats. So, we keep coming up with better and better ways of accomplishing things. But you still have to deal with what's the right tool for the job. Every time I think about power tools, you got like the power, like screw gun, the drill thing that goes really, really fast, but you shouldn't use those on like changing light switches because it goes too fast and then it cracks the plastic. You want to use a manual one for that, but no, I'm too lazy for that. It's a lot easier to go to Home Depot and buy another light switch plate than try again and break that one. So you always buy 3.
I think it's especially screwdriver that have like a mechanized twist.
Right. Or I just call one of my grad students in. They're always looking for extra credit. Okay. But I think that is a fair analogy. I mean, you really want to look at this stuff and kind of appreciate where we are in terms of computers today. Because there is a lot of layers that live between us as a computer programmer, which I've already told you is hard, right? So there's layers that live between us as a computer programmer and actually talking to the CPU. And the good news for us, or at least the better news for us, is those programs are already created. These compilers, things like that, these have already been written that do that mapping for us so that we don't have to. All right. Well, let's just see. I know we got just a couple minutes left. So if we were thinking about what's the ultimate goal of a programming language, it's for us to tell a computer what to do. the end of the day, that's what it is. Getting back to what I said about human beings being good problem solvers, we've also spent our entire life talking to other human beings. So we're very skilled at, telling someone, do this, then this, then this, and communicating with a human being for that. And even if you speak multiple languages, I speak English and I don't know, maybe enough Spanish to order at Taco Bell. For those of you who are actually fluent in other languages, if you're talking to your English speaking friends, you're using the exact same thought process as you might if you're speaking to your Spanish speaking friends. The words that are flowing out of your mouth, the syntax, programming language, might sound different, but ultimately you're expressing the same kind of ideas. You don't convert your way of thinking because you're speaking to, a person from Spain or Mexico as opposed to talking to a person from, Illinois. They're still people, and people operate off of the same kind of logic. You're just changing the sounds that are coming out of your mouth, that type of thing. Okay. So ultimately our job is for programming is to tell a computer what to do. But in order to do that, we have to fill in all those little tiny gaps. Okay. And that's the tough thing. That's what we're not used to doing, is breaking problems down into those little tiny steps. All right. Well, we just looked at that. All right. I'll start here next time. So somebody remind me I'm on this truth slide. So we don't have our first assignment yet. I might encourage you between now and Thursday, make sure you're on the Slack channel. And maybe if you want to get a head start on it so you don't forget, maybe do the first Bible homework or get started on it, something like that. Like I said, it's not due till the end of the term, but don't let it fall off your radar. All right. Questions, comments, concerns, bribes. The bribes kick in midterm, it's like, okay, that exam didn't go well. Let's all right.
What is awesome? Is that yours?
Yeah. So